Alright, it is the fall final review video. We're going to get started right away because this should be pretty long. This first one is talking about just a little experiment. Fish's body fat is recorded on a feeding schedule that will change. So what is the independent variable? That's the feeding schedule. The 3 different tanks have different feeding schedules. What is the dependent variable? That is the body fat of the fish. So just a little scientific methods. The next ones are just some true-false questions, and I'm not going to get into those too deeply. But yes, we want to waft. That's good. The proper procedure for diluting an acid is to add water into acid. No, that is false. You should add the acid slowly into the water. Intensive versus extensive, we want to make sure you do know the differences. Intensive properties are independent, so they don't depend on amount. Independent of amount. Extensive, think of extras. Do extras matter? If extras matter, so if I have more than 1 pen, right? Extras will matter. They will change the mass, the length, etc. So that's intensive versus extensive. We're going to go on to actually page 3, since page 2 is just some really good notes. But be sure to read over those because it's a nice little summary. Don't forget the Sig Fig song. Beginning is never, middle is always, the end, yes, dot, no, dot, no. Want to keep that one in mind. Okay. So on page 3, really want to make sure you can put those in order, especially number 6. It's just one of those things you're going to have to remember. Okay, use what you know about common sense. Think about a millennium. How long is that? It's 1,000 years. Milli, 1,000 compared to your base unit. Same thing with centi. Think about a century. Deca, think about a decathlon or a decade. That's 10 years, right? So use some of your common sense to help you through those, because you really want to make sure you know how to do these. And I will say there's a little bit of just a small error in the key on Canvas. The key on Canvas says 8.5 KL. It was set up, except just wrote down the wrong number right there. So this is the correct answer. But I'll show you how we do our dimensional analysis, because this is a skill you are going to need for this final, as well as extensively next semester and in physics. So basically, you want to box your given, circle your unknown. My given is 104 kilometers. I'm looking for how many meters. Here are my equalities. You start always with your given. Start with your given. That's 104 km. Okay, and then we're going to just go down, right? That just means what we want to make sure we move our unit down here, and then we want to think about what we need to get to. We're trying to get to meters, and there is a direct conversion factor there. So I'm going to write meters up there. And then you just kind of want to use your logic. What is smaller? What is bigger? Okay? A meter is smaller than a kilometer. You know that because kilometer is kind of like our equivalent here in the U.S. We use miles, but same idea, right? So that means for every 1 kilometer, you've got 1,000 meters. And then once I have that nice little setup, I can just multiply what I have on top. So if you just take your calculator, multiply, or honestly, you don't really need a calculator for this one, but you're more than welcome to use one. And don't be concerned if this is a big number. It should be big, right? You're talking about like a meter stick, right? And you're talking about it's going to be larger, so don't worry there. These are just our little setups. If it's 2 steps, that's fine. Just write in your conversion factors. Okay, as far as accuracy versus precision, I drew this little target. This first one is precise, right? We're hitting the same spot over and over again, but it's not accurate because this is the center of our bullseye. Here on this one, we have one single arrow that is accurate, but it is not precise because they weren't able to repeat it. And if you're a very good archer, you can be precise and accurate, which is really what we are aiming for in science. So think of this little picture in your mind, right? Precision is can you repeat this, or how close are your measurements to one another? Whereas accuracy is how close is it to the standard or known value. So if you have a 1 pound weight, it should weigh 1 pound, okay? Those are the differences. Okay. Moving on. Here we are going to record the volume of the graduated cylinder and circle the estimated digit in our answer. So you want to look from the bottom of the meniscus, and you're going to use the hash marks to figure out exactly where that estimation is going to be. So you want to look at the little hash marks, and you kind of have to estimate off the last one. So if I'm looking at this one here, I can see that it's close to, it's getting close to 8. So it looks like it's about, and especially because it's not a very good copy, but I would say you read from the bottom. So it's hitting at 7.8. I know it's a little higher than that, but I'm not exactly sure. That's why that last digit is going to be my estimated digit. Same for this next one. So I read from the bottom. So on this one it's going to be 7.8, and it looks like maybe a little higher, so this is my estimated digit. And I'll just go ahead and write out these others. Okay, so on the next part, writing in scientific notation, this is actually very, very simple. I just have to remember how to do it, so we'll practice a little bit. I'm going to take my decimal point, and I need to move over until I hit a non-zero digit and just count how many times I have to go. So on this one, it is a small number, very small, so I'm going to end up with a negative number. Okay, so here we go. 1, 2, 3, 4, 5. Now I have a non-zero place. I moved the zeros 5 times, and I'm going to write it like that, 7.86 times 10, because that's how scientific notation is always written. And because it is a very small number, it is less than 1, we had to move it, it's going to be negative up there. Our exponent is going to be negative. Now if it's larger than 1, like this one, or that one, same idea, except you're going to have a positive exponent. So again, I need to only have one non-zero digit in front. So if there's a comma there, I'm going to turn that to a decimal and move it 1, 2, 3 times. So it's 3.952 times 10 to the third, because that's how many times I had to move it. Alright, so again, ready, I had to move this one 1, 2, but it's less than 1, so it's 6.7 times 10 to the negative 2. Okay, so we're going to go ahead and turn to the next page. With our standard notation, it's sort of the same process, but in reverse, right? So this one is, I'll show you this one, to the negative 8. That means there should be 7 zeros in front here, because I know it has to be less than 0, so it's a big one. So I'm just going to put my decimal down and count 1, 2, 3, 4, 5, 6, 7, and then I can write out the rest of the digits. And that's how we do it in standard notation. Pretty straightforward. Okay, significant figures. And that's where you want to maybe use your little song. Again, this little song, I'm not going to sing it because I can't sing. Beginning is never, the middle is always, the end, yes, dot, dot meaning the decimal, no dot, no, not significant. Okay, so no dot here, and I see a 0. That only is going to have 2 significant figures. Middle is always, yes, okay. On number 25, these are all trailing zeros without a dot, so there's only 1 significant figure. Middle is always, and there's a dot, so I'm going to count 1, 2, 3, 4, 5, 6, 7. Everything's significant. Okay? On this one, this is an example of leading zeros. These are all leading zeros before a non-zero number. So we have these 3 zeros that don't count for anything because we haven't hit a non-zero digit yet. That's why there's only 3 there. All right. So this next part says calculations in significant figures, but it's kind of weird because this first one I think is just a typo because there's no calculation there. On this next one, we're dividing. So when you divide, you just use regular sig fig rules. Okay. Normal sig fig rules, meaning I just want to get the least amount of sig figs in my answer. This one has 1, 2 sig figs, and this one has 1, 2, 3, 4, 5. They're all significant because of that dot. So I only want my answer to have 2 sig figs. So your calculator answer is going to be different than what you want for your significant figures. So I'm just going to divide. And if you want, I can show you with all the digits in there. Okay, so we only want our answers to have 2 sig figs. So how we answer that, we are going to round it. So here's our calculator answer. It is 7 point, this whole long number, right? But we only want 2 significant figures. This does not round up. So actually, our answer is just going to be 7.0, because remember, if there's a dot there, that 0 is significant. So there's our answer. We went from this calculator answer to our sig fig answer. There aren't any addition and subtraction on here, but I did want to talk about the addition and subtraction rules really quickly. Remember, if it is addition or subtraction, we don't do that same way we do for all our other sig fig rules. We want to use our DAD rule, which means digits after decimal. You want your answers to have the same amount of digits after decimal as the least. Okay, so if we were thinking like, I don't know. Okay, so that has 3 digits after decimal, and let's say we were adding it to 27. This actually has no digits after decimal, so our answer would be, and again, this isn't on your paper, but I wanted to review this really quick. 24. So our answer is actually going to be 28 because there are no, that's what it would be if there are no digits after decimal. So keep in mind the DAD rule. Sorry we didn't give you an example of that. And then I'll just work out number 35. So that one says 787 divided by 3.0. So this is my calculator answer. That is not what I want to use for my sig fig answer though, because my sig fig answer, I have 2 significant figures right there. So I only need 2 significant figures, so I'm going to have to take this calculator answer and just round it to 260. And I'm just noticing now that is another little mistake, because your answer key on Canvas says 2400, and I think it was just typed in wrong. So it should actually be 260. 260. So that would give me only 2 significant figures. So make sure you make that change if you wrote down the key there. There is really no answer to this because there's no calculation there. Alright, so I am going to work out number 37 for you. Okay, so 1 milliliter of ink can print 50 pages of text. We want to find out how much we could print if we had 100 gallons of ink. So I'm going to start with 100 gallons of ink, right? These are my, I'm going to box my givens, right? I'll box my givens. 1 millimeter of ink can print 50 pages. And we want to know how many pages we could print. How many pages? We're looking for how many pages given the amount of ink we have. Okay, so I'm going to start with the 100 gallons and set up my conversion. If I have 100 gallons, I need to get over to milliliters, but there's not a one-step conversion. First, I have to do the just go down, right? So I'm going to bring down 1 gallon. We will give you this, so don't worry about memorizing this, but just FYI, for 1 gallon is equal to 3.785 liters, and we will give you that conversion if you need it. We don't expect you to memorize the imperial conversions. We do want you to memorize your scientific, so like the meter, liter, how many going from one to the other. So this next part you would need to memorize. These units will cancel out. We would expect you to memorize the conversion between liters to milliliters. And in 1 liter, there are 1,000 milliliters. Okay. Now we need to think of what we're trying to get to. Again, you want to start kind of thinking with the end in mind. We're trying to figure out pages. And we know the conversion for every 1 milliliter, you can print 50 pages. So we want to do that step next. So I'm going to just go down, again, milliliters. Every 1 milliliter will give you 50 pages. And now we only have one variable left, and that is what we want to end with. The one you end with should be what you've circled originally. You should only have one unknown. So we're looking for how many pages. And so now we can just do all that math by multiplying everything on top and multiplying things on the bottom. Of course, all our variables on the bottom happen to be this time 1. So really I don't have to worry about anything on top. So I'm just going to multiply. I'm going to say 100 gallon times 3.785 times 1,000 times 50. And here's my calculator answer, but I need to give it in significant figures. So I need to change that to my least amount of significant figures. Now, these conversion factors have unending significant figures. So we don't use that, but we can use this as a significant figure. This only has one sig fig because that 0 is not significant. So my answer, I only want one significant figure. So I'm going to round this all the way up because this 8 would round up to, So I'm going to make this a 2, and it's going to be 20. There we go. So remember, don't use conversion factors to figure out sig figs because technically they're endlessly precise. So this is a conversion factor, this is a conversion factor. This is not a scientific conversion factor. This is the conversion factor I'm using for this particular problem, but that's not like a scientific conversion. So that's our answer. And there's the work on that other problem again, just going from boxing your givens, circling your knowns, and just canceling out your units. Kilometers cancel out. Your miles will cancel out when you do that conversion. Here we gave it to you because we don't want you to spend your time memorizing the imperial system here that we use in the United States, this is 6.22. And again, we're going to use this to determine my significant figures because it's not like a standard conversion, right? It's just the particulars of this problem. This has 3 sig figs, therefore my answer will have 3 significant figures. Okay. So this is just like a quick review of 8-man. The atomic number represents protons, which I'm going to write as P, and neutrons, which you can write as an N0. That is because they are neutral. So you are going to have a lot of problems that are going to ask you to calculate things like number 8. Okay, how many of each of the following? This is going to be really important. This is a critical thing that you need to know how to do. This number up top, okay, this is the mass. This number down here is your atomic number. Do not say this is neutrons. This is not neutrons. This is mass. Mass is equal to protons and neutrons added together. So in order to find the neutrons, we need to subtract. You need to say 123 minus 51. So that is 72. In a neutral atom, you can assume that protons and neutrons are the same. So I'm going to use that atomic number. This is an example of one that is not a neutral atom, okay, because it has a +2 sign. So in this particular problem, we're going to say that there are 10 electrons because this magnesium is positively charged, which means it has lost 2 electrons. So it would have had, would have had 12. It was normal magnesium. I get that because of the periodic table, right? There's magnesium. Normally, these are the same number of protons and electrons, but this magnesium has that +2. So that's where that came from. And the neutrons you can get by taking this average atomic mass. I'm going to round it up to the largest whole number, which will be 24 minus 12. Okay, so that's that. Bohr models are just kind of like this. So for chlorine, oftentimes you'll see them with the protons and neutrons noted in there. So I'm going to find chlorine. Chlorine has 17 protons, and in order to find the neutrons, you subtract again 35 minus 17. So you can write that in there. So it would have 18 neutrons, 17 protons, and then we're just going to start drawing the rings. Okay, so the first ring can only hold 2 electrons. 1, 2. The next one is going to have 8. So that would give us 210. And so we have to draw one more ring, because it cannot hold more than 8. And so we'll have one kind of single electron, and that will equal 17. There it is. Okay. So, moving on, we're going to head over to page 7. Okay, atoms of the elements that are in the same group have the same number of valence electrons. This is probably something that you've forgotten how to do, so I'll show you that really quick. First thing you want to do is for each step, take this number here, the mass. You're going to multiply that by this, but you need to change it from a percent to a decimal. So this is percent abundance. You do that like Dr. P, right? Percent to decimal, you're going to move over 1, 2. So that's going to go like that. You're going to multiply those. So here's the work. 27.977 times 0.9223. And that equals 5 Same thing. I'm going to keep going. Remember, move it over 1, 2. Tricky on that one. Don't forget. Don't put it in as 0.4. And finishing up. And then what do you do to finish it off? You need to add them all together. So take these numbers, that 25.803 plus 1.3531 plus 0.92912, and that's going to give me my percent abundance, and that is going to be 28.08522, but we're going to change it a little bit to account for our sig figs using these. So our answer that we're going to use is 28.086. And one can make an argument about sig figs with this because these could technically be endlessly insignificant, but we're going to use that. Okay? All right. So this is going to be something that you are really going to want to know how to do quickly. This should be very simple, fast. Least reactive, that's going to be my noble gases. Most reactive metals, that's our alkali. Our most reactive nonmetals, those are the halogens. So here we go. You should be able to number these really quick. This is 8A. That's where our noble gases are. These are our halogens, 7A. 1A, that is our alkali. 2A, that's our alkali earth. Second most reactive. Transition metals, that's basically this whole area until we get to like our stair step. So our stairs here, that is going to be the marcation of like our metals from non-metals. So this whole part, everything shaded here, those are our transition metals. So then we can start counting them up again. So this is 3A, 4A, 5A, 6A. All right. And kind of like our metalloid areas. Can do that. Different color maybe. Okay. So we want to do our trends as well, right? We'll do the trends. You should be able to do this really quickly. Our trend going to atomic radius, heading towards francium cesium as the largest atomic radius. Electronegativity is headed the other direction. And stops here with fluorine. Fluorine is the most electronegative. Noble gases have no electronegativity because they already are perfect as is. They do not need any more electrons. And remember, electronegativity is a measure of how much do they want an additional electron. Noble gases don't want that at all. This is different than ionization energy, which is headed the same way, but is all the way to, this is our highest. The noble gases have very high ionization energy, and I like to remember ionization energy is, there is an I in ionization energy, and our noble gases are all about themselves. They love themselves. They're perfect as are. So perfect as is. They do not want you to take away an electron. They're very happy with the way they are. So you should be able to quickly draw that out, like day of your test. you want to be able to recreate that if you need to very quickly. Okay, page 8. Okay, I'm going to let you do the properties of metals versus nonmetals because I think you all can do that yourselves. Okay, alpha, gamma, beta, it's been a while, but here we go. Here's my alpha symbol, my beta. My gamma kind of looks like a Y, kind of. These are Greek letters. Alpha you can block with paper. Beta you're going to need like thin metals or gold sheets, aluminum, something like that. Gamma you're going to need some thick concrete. Those are your bunkers. So those are the most penetrating gamma. Number 1, most penetrating, that's what makes you turn into an X-Man or a Hulk, right? That's the bad stuff, the gamma. Second most is beta. Least, of course, is the alpha. Oh, this says lead, and that's true. So concrete or lead work. That's like when you go to the dentist, why they make you wear those little lead aprons, or if you've ever gotten an X-ray, when you get a dentist X-ray or get an X-ray in general, lead and concrete will both block that. Least damaging. So be aware of least to most, and don't rank them wrong. These are actually the keywords down here for the little graph here. So I'll show you that. Fusion occurs in the sun, so helium and the hydrogen will turn into helium, which is much more stable. That's a fusion reaction, so they get from lighter to a little bit heavier to make them more stable. These aren't as radioactive, but they do have a lot of energy. Both of them release a large amount of energy. Fission reactions are a little bit different than fusion. So in fusion, they're unstable because the center of the atom is a little bit too light. These ones are too heavy, so they get rid of some extra energy by splitting off, or not extra energy rather, they produce energy as a result, but they get rid of extra weight from being too heavy by splitting off into lighter. So these are more harmful. This waste is more harmful, and I'm just writing this in. And you see this at like nuclear power plants and atomic bombs. These release a large amounts of gamma radiation, whereas your fusion reactions do not. Okay, lots of energy, but not gamma radiation. Okay, so just a quick review on how we do these. You're not going to be responsible for gamma, because gamma is a little bit more complicated, another ball of wax. But you should be able to recognize this is an alpha particle, okay? This is an alpha particle. Anytime you see that 4,2 helium, you know you're undergoing some alpha. This is alpha. So what's on the left is equal to what's on the right. So think to yourself, 240 plus 4, that is 244, right? 94 minus 92, that is 2. Okay, so from there you need to pick draw in the helium. Same thing on this side. Don't make the mistake of not checking your work, because a lot of times students will rush and put like 52, but think about it, right? If you go back in and check your work, 52 plus a -1 is not 53, okay? It is 54. And also keep in mind, anytime you change the atomic number, you're changing the element itself, right? So plutonium, 94, where are you? 94, here's uranium, there's plutonium. So see how if I change this number here, I've changed the element. Same thing with this one. It's going from iodine, 53, to 54, which is xenon. Okay? So if you change the protons, you change the element itself. Okay. Moving on. these are little important details that this is talking about just about the totals. Really, it depends how you're thinking about it, but the first one can only hold 2. It's very small. After that, 8. The next one, 18. The next one after that, 32. And then the one after that is 32. Although, typically, like when we draw our little Bohr diagrams, we don't really make you go past the third, because that would take forever. And also, you're not going to be drawing out a Bohr diagram, most likely. But you do need to be able to identify them. So, how many electrons can each sublevel hold? This goes back to our electron configuration. 2 on the S, 6 for P, 10 for the D, 14 for the F. Okay? Electrons will always fill the lowest energy level first. Always, always, always. Okay? The lowest energy. Which one's lower here? It's actually 4s. Even though, remember, they go a little bit out of order because of the way the periodic table is working here. And that's kind of why you see the dip with the transition metals. So, S fills up first. It is lower energy. D will fill up before P. It is lower energy. Even though 5s is afterwards, it will fill up first. Keep that in mind. Alright, so what is this? If you see designation 3D8, what are we talking about? The 3 represents the principal energy level. The D represents the sublevel, right? So that's like this part. And the superscript 8 is representing the electrons. Alright, so if we're doing electron configurations next, I know it's been a while, but remember, you can take the little periodic table and think to yourself about the S, P, D, and F blocks, although we usually don't make you go all the way down to the F block because those are so long. Alright, so for sodium, always start at the beginning. Almost everything except for hydrogen will start with 1s2. 2s2, 2p, 2p, let's see, where is sodium? 11. So we need to count and make sure these numbers get to 11. So we know the next is going to be 2p6, so keep track. We're at 4. If we do 2p6, it's full, right? And that gets us to 10. We need one more. So that is 3s1. And if you look at the periodic table, that makes sense because 3, and this is the S block, S1. Okay, so I've filled them up. Don't forget to move all the way across. 1s2, 2s2, right? 2p, and it goes in order, so go from 4 to 5. 6, got to the end, that got me to neon, which is number 10, and we need to finish off at sodium, 3s1. All done. Okay? Our noble gas configuration. For a noble gas configuration, you want to, again, look at the periodic table. Here's sodium. I want to find the noble gas that is the closest without being larger. So I'm going to use neon, because neon is number 10. I cannot use argon, because that would be going backwards. Okay, so my noble gas configuration, I'm going to say argon, and then I only have to finish off the configuration from argon. So this is argon's configuration, right up till the 3s1. So if I put it in the brackets, that represents argon, and then I just have to finish with what's left over. Okay, the orbital diagram, that's just taking this and turning it into arrows. So I'm going to say 1s up and down, because they cannot spin in the same direction. The electrons, and the arrows represent electrons, so I have 1, 2. 2s up and down. 2p, up, down, up, down, up, down, and that's 6. 3s up. Okay, So that is how we're going to do those. So we're going to go leave off with this first video, and we will get some more done later, but that got us all the way to page 10, so it's a pretty good start. And we'll see you in a little bit.